So far we've talked about experimental probability and some sample space matters. And now let's talk a little bit about the theoretical probability. This is the idea that we can come up with probabilities or likelihoods of things happening without actually having to perform the experiments. So consider here we have some spinner, and this is symmetrical spinner. So every single wedge has the same amount of space, so that when it's spun, the arrowed marker right here should finish and could finish with an equal likelihood on each of the sections marked 1 through 8. And the key here is that there's an equal likelihood that all of these things could happen. So if I were to say the likelihood of obtaining the outcome of a 4, landing on a 4, it is 1 chance out of 8, or 1/8 of a chance, or 12.5% chance, or we could say 0.125 probability. All 4 of these things represent the same general idea of the likelihood of this thing landing on a 4. This is a mathematical or theoretical probability, and it's based on what we theoretically expect to occur. So it is the chance of the event occurring in any trial of an experiment. So it doesn't mean that it will. That just means that is the chance of it happening 1 out of 8. It doesn't even mean that if you were to do it 8 times, you would definitely land on it once. It's just the theoretical probability of this happening. So sometimes we actually would need to perform the experimental probability many times in order for it to approach that theoretical probability. So what if we were to say, well, what's the chance of spinning a 6 or higher? Well, in this case, we have to think about what the favorable results are. It could be a 6, a 7, or an 8. That is success in this matter. We have a sample size of 8, since there are 8 wedges. And since each space is equally likely, we could say that the probability of spinning a 6 or more is 3 out of 8, since there are 3 favorable results out of the possible results. So we can come up with these theoretical probabilities quite simply if we know the favorable results and the sample size. So in general, if we have an event A containing an equally likely possible results, the probability of A occurring is the number of members of the event A divided by the total number of possible outcomes. This is like the number of members of the event A could be 6, 7, 8. So there's 3 of them, that's the number, divided by the total number of possible outcomes, which would be 8 in the previous example. So let's talk about this example 5. We have some ticket randomly selected from a basket containing 3 green, 4 yellow, and 5 blue tickets. We want to determine the probability of all of these items. So let's start off with green. Let's go green for green. The probability of getting a green ticket. Well, actually, first thing I should do is let's go back to purple here, and let's find out the total number of outcomes. So the total, what did I call it before? The total number of possible outcomes. So total, that's an L. Outcomes is going to be, there's 3 plus 4 plus 5 tickets. So 3 plus 4 plus 5 tickets, and that's equal to 12. So there are 12 total outcomes. That means that the denominator of all of these probabilities should be 12. So to pull a green ticket out, there are 3 green tickets out of 12, and that's going to reduce down to 1/4 of a chance. For a green or yellow ticket, let's stay green here, that's going to be, if I can pull a green, so I'm successful if I pull a green or if I pull a yellow. So that means that I'm successful if I pull a green out, that's 3 of them, or if I pull a yellow out, that's 4 of them. Either of these things happening is success. So it's kind of like when we were spinning a 6 or a 7 or an 8. We kind of add those items together. And so then that's out of 12, so that's going to equal 7 out of 12. So there's a 7 out of 12 chance that I'll draw one of those things. Let's go to orange. The probability of grabbing an orange ticket, let's write it in probability notation. The probability of grabbing an orange ticket is, well, there's no orange ticket, so that's just 0. That's definitely not going to happen. It's impossible. And then finally, the probability of green, yellow, or blue ticket is, well, that's all of them. So that's 12 out of 12, which is equal to 1. This is definitely going to happen. Once I reach into this basket, I am going to pull out either a green or a yellow or a blue ticket, definitely. So why don't you try this example here. 6-sided die, rolled once, determine these 4 probabilities. So pause the video, give this one a shot. Okay, so here are my outcomes. It's important to come up with that sample space, and then to find all those probabilities. Take the number of favorable results, divide by the total sample space, and there you go. And we're going to highlight a couple of pairings of these things. So take a look at A and B, and take a look at C and D. There's a link between these two things. And what I want to talk about before we pause this video before the next one is I want to talk about complementary events. In that last example, you might have noticed that the probability of 6 plus the probability of not getting 6 is equal to 1. Similarly, the probability of getting a 1 or a 2 and added to the probability of not getting a 1 or 2 is also equal to 1. Interesting. We call these things complementary events. They complement one another. And what that means is that only one of these events must occur, exactly one. In fact, it's impossible for both events to occur simultaneously. And think about that. I can't roll a 6 and not roll a 6 at the same time. I can't roll a 1 or a 2 and not a 1 or a 2 at the same time. So these are kind of like in contrast to each other. And so we call them complementary because it's like one must exist while the other does not, type of a thing. So in general, I could say two events are complementary if exactly one of them must occur. And we can use this probability notation of saying the probability of A occurring plus the probability of, this means not A occurring, is equal to 1. I can also solve for a probability of A not occurring, and that will always equal 1 minus the probability of A. And you can think about that like I subtract this probability on both sides and I get this. This is actually going to be helpful sometimes when we are trying to find really complex probabilities. Sometimes it's helpful just to subtract something easier from 1 to get that probability. And we'll get down there in a second. So in the next couple of videos, we'll talk more about these complementary events.